Welcome to more live notes, which Neil is 100% ready for.
Yes.
All right. So each of these experiments is designed to show you something important. So like eventually when you do these on your own, like try to do them with your group and then decide what was I supposed to have learned based on this experiment. So, but let's do experiment 0 together. So you can totally do this kind of thing. You can make a function whose input is a number, but whose output is a vector. And that's new, because usually functions like the input's a number, the output is another number. So like what would this even look like to do? Let's try and like make a data table, because that's the easiest way to explore it. So at time -2, let's see what happens when we plug in -2 to the vector. We get -2 times the vector 2, 1, which if you wanted to like expand it out would be -4, -2. Okay, let's draw like a little tiny picture of the vector, kind of a not to scale picture. We're going to be using what we call position vectors. What a position vector is it's a vector that always starts at the origin. And the reason it's called that, let's draw it up here. So if we have a position vector that's 2, 1, remember 2, 1 is a vector is like a motion. It means over 2, up 1. But you could start it anywhere. But if it's a position vector, we're going to start it at the origin. So if we go over 2 plus 1, now it points to the coordinate 2, 1. So there's like kind of a subtle notation thing here. Triangle brackets are not referring to a point in the plane. Triangle brackets are referring to the motion of wherever you start, go over 2 and up 1. Parentheses are referring to a particular location in the plane. And then these are connected because if your motion starts from 0, 0, then this motion points to the coordinate that has those same numbers. Is that weird or is that okay? Okay, it might be weird, but that's, you can ask me. Okay, so now that that's clarified, so what is this vector, -2 times 2, 1, like what does that actually look like? Well, if this is the, let's name this vector v. It's nice to have a name. So if this is the vector v, here it looks like I've flipped it the other direction and scaled it by 2. So as like a little sketch, it would be like this, right? It's like that vector twice as long in the other direction. Okay, let's do another one. So if time, and that was time -2. If time is -1, it's just the opposite of 2, 1. So if I'm going to sketch a little sketch, it's still flipped around, but it's sort of half as long as this one was. Okay, what about time equals 0? So time equals 0, I'm scaling the vector 2 by 1 to be length 0. We haven't really talked about how would you notate this. How do you want to notate it? Yeah, just a dot. Because if you have a vector that's starting here, but its length is 0, like that's it. It's just there. It's just a dot. Okay, so if time is 1, it's just the vector 2, 1, which is going to be pointed like this way. And then if time is 2, it's scaled to be twice as long, like that. Okay, now's the time when you have to like use your imagination. Yay! So here, I really want to gesture to the board. Okay, I'm going to gesture in the video. Do you guys ever make flip books when you were kids? Like little animated flip books? Imagine that you had like a joyful childhood where you made flip books, and then imagine that you are going through this sequence of images. Imagine it as an animation. So as time goes from -2 to +2, we have a vector that starts out kind of long in this direction, and it's getting shorter and shorter, approaching 0, and then it's getting longer and longer going that way.
What was the need for?
So we have an excellent question, which is how, I started the video again, which is what would this be as a regular old Cartesian equation? Let's imagine the sequence of points that the vector points to. So at time, so here, why don't you sketch this together, because notes. So at time equals -2, the vector is pointing here at -4, -2. That's time equals -2. At time equals -1, the vector has shrunk, so now it's pointed here. At time, so this is time equals -1. Here's time 0. Here's time 1, it's pointed here. Here's time 2, it's pointed here. So hopefully you can see that as time grows continuously, we're going to point to every single location in between along this line. So this is a vector way of defining a linear equation, and the question is, what linear equation is it? Well, what's the y-intercept? Okay, 0, and then what's the slope? Yeah, 1/2, because I'm going over, like I'm going up by 1 for every 2 I go over. So if slope is like change in y over change in x, that would be 1 by 2, as we say. Cool. I like it. So just to be real clear here, so here was the vector that we're time scaling. What I mean by time scaling is as time changes, the vector is growing and shrinking. So this was change in x. This is change in y. We know that slope is change in y over change in x. So like literally, you know, it's just 1/2. Again, okay, the video has started. Experiment 1. Oh, hold on. So experiment 1, very similar concept, except this time our vector equation, the time is inside some trig functions. But let's not stress out about it. Let's go plug in some numbers. Let's see what it looks like. So if I plug in 0 here, I've got cosine 0 and sine 0. And then in my extra column, I'll actually evaluate that. So cosine of 0 is 1, sine of 0 is 0. So if I'm going to make a tiny sketch, my vector is length 1 pointed this way at time 0. Okay, what about time pi over 4? So cosine pi over 4, sine pi over 4. So let's see, cosine pi over 4, I got to draw my unit circle to think about this. Okay, so it's going to be root 2 over 2 and root 2 over 2. And so that's going to point this way. You should be thinking animation in your mind. Time 0, I'm here. Time later on, I'm up here. What's the length of this vector, do you know? Maybe. Yeah, maybe. Could be 1. Okay, so time pi over 2, I'm just going to jump straight to evaluating it. So cosine of pi over 2 is 0. Sine pi over 2 is 1. So now the vector is pointed up. 3 pi over 4, I'm going to be at negative root 2 over 2. Root 2 over 2. And so now the vector is pointed that way. Last one at pi, my x-coordinate, cosine of pi is -1. Sine of pi is 0. And so I'm pointed that way. Okay, so same thing. Imagine this vector changing from here to here to here to here to here as time moves forward. All together like one chorus of voices. What shape do you think it's making?
A circle.
Here we are in experiment 2, which 7th block has mostly invented already in experiment 0, so I'm just going to talk it through here. Okay. So let's think about this new vector equation. It's similar to experiment 0. Experiment 0 was like this, right? We just had a single time-scaled vector, and we thought about it as, let's imagine what that vector looks like, but then as time changes, it's like growing longer and shorter. And so it's going to trace out a line. As we were saying last time, a nice way of thinking about this, let's call this A. Let's call this vector A here, and let's call this vector B. So if we imagine vector addition, like A plus a scaled version of B, so if time equals 0, then the scaled version of B just becomes 0, because 0 times anything is 0. So at f of 0, we have just the vector 4, 3, which points here. So go ahead and draw out that A vector. Okay, so now I don't have a place for you to make a table because I don't think we want to make a table anymore. Instead, we just want to imagine this other vector being time scaled. Let's maybe just do 1, okay? So f of 1 is going to be 4 comma 3 plus 1 times negative 1 comma 2. So let's just draw them separately. Here we've got the 4 comma 3 is A. Negative 1, 2 is going to be here. That's just the B vector. And if we imagine the vector sum, which I want to imagine in pink, here we go. So the vector sum is this new vector that points here to this ending spot. If we imagine time is 2, the A vector stays the same, but now we're adding this B vector that's been scaled to be twice as long because time is 2. So if B is scaled twice as long, that takes us up here. And so the resultant vector is this, but it points there. If time is 3, the resultant vector is pointing up there. If time is negative 1, the resultant vector, here's like negative b because it's like the other direction. The resultant vector points here. So like all of these pink vectors, again, like let's imagine the animation. If time is 0, we got the vector pointed here. As time increases, we're imagining this vector kind of getting longer and like pointing up along this line. Instead of plotting all the vectors, let's just plot the set of points where they're pointed towards. And they're just like all along this line. So long story short, we have come up with an equation for this line. Well, I'll come back in post-production and like fix that. But this is a vector equation for that line. Okay. What's the learning? I guess here's the learning. The learning is, well, let me ask you a question. Could you come up with another equation like this based on vectors and time that also sketches this same line? The video. All right, so suggestion on the table. How could we draw another equation that also traces out this line? This was the proposal. So let's start at 4, 3. So this A vector is the same. But as time changes, we're going to be moving along the vector negative 2, 4. So let's think about that. So when time equals 1, negative 2, 4 would be, it's still pointed along the same line. It's just twice as long. So what that means is that in the old equation, when time was 2, we were pointed here. In this new equation, time only has to be 1 to be pointed to that same spot. So yeah, I think this equation still works. Okay, video started. Could we do the same equation, but not involving the vector 4, 3? The suggestion was, yeah, you can have a vector that just points to any other point on the line, and then add a time-scaled vector that points in the direction the line is supposed to go. That's the big learning. How could we write it down? My note sheet is poorly designed. So this could be like any point on the line, and then this is a time-scaled, so like time times any vector along the line. Wow. Can you read it? Sort of. There we go. So that was the big learning. Okay, let's round it out. You may, like, this is the big culmination. You may need these things to do your homework. It would behoove you to write them down. Too long didn't listen, write this down. So we know, all right, so I've reminded you from experiment 1, this vector equation, as time increases, is just a vector whose length is 1, just rotating in a circle. So this defines the unit circle. So how would I do it if I wanted a circle that was length 5? It's like, oh, like how, like I want the motion of the vector to remain the same. It's just like I want a longer vector. So let's scale the vector by 5. So the solution to this one is just 5 times that original unit length vector. Cool. And you can draw your, your hearts and your smiley faces. Okay. What if we want to like center it somewhere else? So this is the idea from experiment 2. Like remember experiment 0, we had a line, and then we realized you could add an initial position vector, and that would like translate the line somewhere else. So let's just apply that exact same idea to this. So I'm gonna have f of t is gonna be, let's start it at, where's our favorite place to start it? 4, 5. But just I love 4, 5. It's my favorite. Okay, so let's think what would happen here. What would happen here? So we're starting at 4, 5 is like up here-ish somewhere. So here's 4, 5. So no matter what time is, I'm always starting by moving along this vector. But then depending on what time is, I've got this second vector that's rotating in a circle. So it's going to trace out a circle whose center is that initial location. Cool. That's the bell, the end. Okay, class is over. I'm recording the last 2 minutes. People were pointing out on the way out the door that my circle was supposed to be radius 5. So just like in the last problem where we scaled the rotating vector by 5 to make it length 5 before it rotates, same thing. Let's add a scale factor of 5 on the outside. But the general idea is still the same. It's like start at a particular vector, and then we're going to follow along another vector which is moving. So one stationary vector plus a moving vector, and the endpoints trace out the circle. Okay, could I trace out this line using 3 different vector equations? So let's just like sketch the line, just based on the Cartesian equation. So you've got a y-intercept of 0, 10, and a slope of -3. So it looks sort of like this. So using the ideas from experiment 2, one thing we could do is say, let's start here at the y-intercept. So let's start at the vector 0, 10. And then let's add a time-scaled vector that's pointed along the line. So I could say when I move over by 1, I move down by 3. So 1, -3. And then for different values of t, this is going to be length, length whatever this is, or twice as long, or 3 times as long, or 4 times as long. So I'm tracing along the line. What's another equation I could use here? Let's figure out a different starting point. Let's imagine x is 3. So if I plug in x is 3, y value will be 10 minus 9, which is 1. So I know that 3, 1 is along this line. So I could draw a vector that starts at 3, 1, and then I'll have a vector that points along the line that's time-scaled. So I could write the same vector, 1, -3. If I wanted to, let's see, over 1 and down by 3 is the same as left by 1, up by 3. So when I say the same, I guess what I mean is it's just pointed in the opposite direction. It's like I've multiplied the vector by -1. So because it's pointed along the line that I want to be tracing, for different values of time, it's going to scale along that line and still trace out the same line. So I'll leave the third one for you to fill in, but long story short, it could be like any point on the line, or rather a vector that points to any point on the line, plus time times a vector that points in the direction of the line, points along the line. Okay, last one. Trace out a circle of radius 5, centered somewhere else. Well, we know how to do that so far, because that's what we did in part B. So let's just write that much. So let's center it at 1, 1. Radius 5, I'm going to scale it by 5. Oops. And then if it's going to be a circle, I know it's got to move in a circle, like this, cosine t, sine t. But how do I make it move clockwise instead of anti-clockwise? So the reason it was moving anti-clockwise before is because because time was functioning as the angle. So as the angle increases, like the way we've defined angles is increasing angles are always wrapping this direction from the horizontal. So if we want, when time increases, for the angles to go the other way, an easy thing to do would just be to make them be, make the angle be the opposite of time. So if time was pi over 4, our angle would be negative pi over 4. If time is pi over 2, our angle would be negative pi over 2. So this vector is still moving in a circle, just a circle in the opposite direction. I hope that this was helpful.